Can I start? Okay, so Ami asked me to give this talk, and I thought, I could just give my usual talk of giving an overview of quantum machine learning, and Ami was like, no, that's not going to work. I should give a talk on one of my latest results. And I was like, okay, that's going to be a challenge because this is merely a machine learning and deep learning audience, and I have to talk like a fair bit of quantum physics. So we'll see how it goes. And so when you think about quantum computing, it's conceptually not that hard. So a quantum state is just a very special probability distribution. And a quantum computation is nothing but a transformation of this probability distribution. So basically, if you're interested in solving a problem, what you should do is just encode a solution in some probability distribution and just map it to a quantum calculation. That's it. Some of the tricks go into like how it maps to linear algebra and how you come up with an algorithm. But like this type of quantum calculation is for quantum computers, which we do not have, and that we are not going to have in 10 years, and maybe we have a few of them in 20 years. So this is the very idealized quantum computer that is eternally 20 years away. It's like artificial general intelligence and fusion power. So 20 years from now, we will have all of these three things, but right now we don't have them. So the quantum computers that we have today are noisy. They interact a lot with their environment, and they are very limited in scale. And to understand what it is that you can actually do with these, you need a lot more physics to figure out like what is the relevant algorithm that you can execute with them. So this second paradigm, so what is pragmatic today for certain kind of application areas is the stuff that I'm not going to talk about today. Because what I'm going to talk about today is Bayesian deep learning on a quantum computer. And it started off really as a bit of a joke. It's not working. I can't.
How many times have you pressed it?
20. Okay. And so it started off as a joke. We just won an award like a few days ago, on the 4th of October. And so, I've been tracing the field of quantum machine learning since the very beginning. And there were 3 papers coming out 5 years ago over the summer. And I got very upset about them because they were all targeting some very abstract algorithm and this future quantum computer that we don't have. And the paper just violated basic machine learning principles. So I was very upset about it. I got so upset about it that I started blogging and trying to first of all understand the papers and then like tell people why they don't make any sense. And then that somehow landed me a book contract. So I ended up writing the first book on quantum machine learning. It was born out of anger. but it didn't stop physicists from writing more papers in a similar vein, completely ignoring what machine learning is about. And so there were 2 themes going around. One was mapping everything back to matrix inversion. So you took some, that's the book. So whatever machine learning algorithm you had, you like twisted it until there was some matrix inversion, and then suddenly you got an exponential advantage. And the other like crackpot research was like, hey, let's build quantum neural networks. And so, I never published a paper on quantum neural networks, so using this absurd matrix inversion algorithm. So I was like, let's do one. Let's do some, deep learning neural network with quantum matrix inversion. And I found like 3 co-authors to play along. And then we finished the paper, and we submitted it to NIPS. The referees hated it. On the other hand, IBM loved it, so they gave us an award. Because we used the 2 quantum computers in executing the protocol, and one of them was IBM. So which makes me think like how bad the other papers must be. So the goal of this talk really is to give you a sense what is like a bad example if people take themselves too seriously when they do quantum machine learning. And then I'm going to give you some pointers what would be like a more meaningful directions to pursue. Okay, so what's wrong with quantum machine learning really? So this is what I mentioned, 2013, there were these 3 papers. And since then, like, this has been the growth of papers per year. So in 2014, there were maybe 25 papers, and you know, they grew to about like 60 papers a year, which by machine learning standards is next to nothing, but by quantum physics standards, like, this is huge. But like, the vast majority of the papers are just not asking the right question. So these are mainly physicists writing about, you know, how they can advance machine learning that they don't understand. And it shows because, you know, this is the total number of papers published in quantum machine learning, and 2 of them were published in machine learning outlets. So machine learning journals and conferences don't take these papers because they're just not interesting to the machine learning community. And
or maybe they don't understand what's.
So I tried many times, right? I always submit at the NIPS some fun paper, and there are 2 cases. One is that they don't bother understanding like the formalism, and it's not hard. It's just linear algebra. It's the same thing as you would use otherwise, but it's written slightly differently. And they're like, Jesus Christ, I'm not going to understand this, and then they just straight away reject it. And some of the other comments are like more valid. Hey, you know, you could do this and that classically. That's fair enough. Yeah, so the first step where most of these algorithms go wrong is something I would call quantum basic linear algebra. What's S? Basic linear algebra subroutines. That's right. And you know, quantum states are there are 2 ways to look at them. One is that they are a probability distribution, and the other way is that this is just some vector in some high dimensional space. But you know, machine learning, you deal with high-dimensional real spaces, and these are high-dimensional complex spaces. And quantum computing is, you know, is just a transformation of these vectors or these probability distributions. So in principle, there are many, many linear algebra routines that you can just map to a quantum computer, and you know, most famously the quantum matrix inversion, that you can do exponentially faster. But the problem is that you need this like a really ideal quantum computer that we are now going to have for 20 years. And to give you just a rough idea of how bad it is, like if you calculate the circuit depth, like how many gates you would need anything between 1 million and 100 million gates to execute this protocol in a non-trivial sized matrix. And you know, and where we are now is if you have more than 10 gates, then your calculations go to hell. So there's your exponential advantage. So this is what you're going to see spelled out later and see experimental results. And the second thing is that, you know, quantum neural networks. Like every time I saw a paper on quantum neural networks, I was tearing my hair out. So it's just typical, you know, just, you know, take your deep learning neural network, put all weights in superposition, and then apply this algorithm called Grover search, which allows you to find the global optimum quadratically faster than you would do it with some classical resource. But I mean, guys, we have 16 qubits, right? So you can, if you take a neural network, you know, every single weight is represented by a 32-bit precision number. So you can embed half the weight on a quantum computer. And you can put it in superposition, fine, but that's not going to give you anything. So it's completely absurd. And the second one is like build some you know, very vaguely defined quantum optical system. The photons going all over the place, interfere them, and then somehow it's a neural network. That's also absurd. And you have no idea how many papers there are out there, like 100. And
quick question, and maybe you'll address it later if someone just disregards the question. But like in computer science, there were also like the computing theory was just a theory before we had, you know, like the technology that we have today. So is it not like do you blame them for futuristic thinking, or is it what is it particularly there?
No. So I agree with you that theory should be there. What I argue about is that like 90% of the research done in quantum machine learning is in this dead zone. So you can do like very theoretical research, like in the early days of theoretical computer science. So for instance, there are very beautiful results in generalizing results from statistical learning theory to the case where you have quantum resources. But only a handful, like maybe a dozen papers, and they're really good. But like a lot of stuff is missing. And people don't focus it because it's hard. And then the other end, where it's interesting, is like what you can do with the quantum computers we have today. Because that's pragmatic. And then you can actually contribute something to the machine learning community. But most papers end up in this dead zone where you need these idealized quantum computers that you cannot execute for a long time. That's my problem.
Fair. So they don't address the more immediate concern.
Yeah. So either go purely theoretical and write beautiful, deep results, or go practical, but like in between is this no man's land, really. And then, yeah?
Sorry. But to the point you made, like some stuff, like linear programming came at a time where people actually kind of used pen and paper in a certain sense. So it was not meant to be run on computers, but then it was not purely theoretical. It was for the army, like, I don't know, supply programming problems.
Yeah.
But then an actual like human computers used to run it, but then like in 20 years time, digital computers started running it. So I don't see that like distinction being material in a sense.
When it comes to this particular algorithm, this particular algorithmic primitive, which like 50% of the quantum machine learning papers use, like this 200 plus, to invert a non-trivially sized matrix, you need more particles than what's available in the universe. So I don't think we'll overcome that fundamental limit. Because we would have to spawn new universes just to invert a matrix. So that's why I'm a little bit against this algorithm.
Yeah.
And then you end up with like completely crackpot quantum neural networks that says that human brain is some quantum cognition system, and people consider connections to black holes. It gets really messy. So this is this combination of like quantum matrix inversion and quantum neural network, which I thought in a single paper we can make fun of both, and that's what we did. And so why quantum enhanced machine learning? So why would it be interesting then? Because so far I've been advocating against this. So I'm not against quantum machine learning. Obviously that's my research field. I'm against this dead zone. So when you think about like what goes into like contemporary machine learning, you use a bunch of different technologies already, right? So you train your neural networks on the GPU, but you want to bring down the power use, so you use FPGAs, and once you train the network, you can just load it on some chip, some application-specific integrated circuit. So my conjecture is that these early quantum devices could become part of the mix. Because there are certain operations that you can do in them that are just inefficient on any of these classical circuits. So these are the kind of things that are really easy to do on like classical hardware. So supervised discriminative problems, which give you some deterministic answer that are easy to parallelize one way or the other. And there's stuff that's harder. I'm not saying impossible, but harder. Unsupervised learning, learning a distribution, a joint probability distribution, and giving you samples, probabilistic stuff, and things that you cannot parallelize easily. And it turns out that this early quantum hardware that we have today is good or could be good for some of these tasks, but not this dead zone research, really. And so for the algorithms that are relevant for using in machine learning with the quantum computers we have today, take classical data and output classical data. The algorithm I'm going to talk about today is more abstract. So it needs to start from a quantum state and it must end with a quantum state. And if you start from classical data and you want to extract classical data from this kind of mindset, then all your exponential advantage goes away, even if you have a perfect quantum computer. Because then what you have to do, first of all, you have to run something called a quantum state preparation. So you have some vector that what you want to encode in a quantum state. The quantum state is also some high-dimensional vector. So in principle, like mathematically, it's very easy to write down that, hey, now it's a vector in Rn, now it's a vector in Cn. But when it comes to an experimental protocol, like preparing a quantum state can be arbitrarily complex, because quantum computation is about preparing quantum states. So if it's some very intricate vector that you want to prepare, then you might need a very deep circuit to prepare it. It's an open research question. And again, so this circuit can be so bad that it can kill your exponential advantage. And this is the easy part. The hard part is to get your calculation out. So at the end of your calculation is a quantum state, and if you want to extract what this quantum state is, then you have to run your calculation over and over and over again, because this quantum state is a probability distribution. So if you just measure it once, you get one sample out of that probability distribution. But that's like flipping a biased coin once. That doesn't tell you anything about the bias. You have to keep flipping it and collect statistics to understand what those biases are. The same thing with a quantum state. You have to measure it over and over again. What that means that you have to end up with the same quantum state over and over again. So you have to execute your full calculation again and again and again. And then you can do something called tomography, which is basically the reconstruction of your quantum state with classical information. So that's how you get classical information out. And this is massively expensive. So don't do this. So if you see anywhere claims of an exponential advantage with quantum resources, an exponential advantage can only happen if you start from a quantum state and you end with a quantum state. If you want to do something classical, then there's a significant overhead.
So question, my impression might be completely wrong, but like, aren't most quantum algorithms, like, you have to do like state tomography on the output, but the design of the algorithm is such that that state is very peaked towards like some classical limits, so like your measurements are very likely, or you're not going to need to run it like 300,000 times and then do a very hard, like complex computation on top. Like, isn't that the case in general?
That's true for the algorithms that give you something called a Grover-like speedup, which is this quadratic speedup. But for exponential advantage,
for sure, like it's not like that. Like that's what you're saying. Like Shor's algorithm is not.
Like Shor's algorithm is it starts with a quantum state and ends up with the factorization is also a quantum state. Yeah. So you have to be very, very tricky with exponential algorithms. And so where do you get quantum data from? You could just load it in a quantum RAM, except that it cannot be built. So there are all sorts of proposals how you would build a quantum random access memory, and there are many ways to attack the very idea of a quantum random access memory. And so one of them is that you cannot clone, you cannot just copy a quantum state. So that's also why you have to prepare the same state over and over again with running the calculation again and again, because you cannot copy it just to make more measurements on it. So unlike classical data, where it's the most natural thing that, hey, you take your random access memory, you have some address, then you just make a copy of the data there and bring it to the CPU. You can't do this in a quantum system because you cannot copy quantum states in general. It's a no cloning theorem, which was, I think it was published in 1981. It's an interesting story why it was probably so late, because quantum mechanics has been around for, even by then it has been around for 60, 70 years. But that's when it was published. People sort of knew it, and you just cannot easily duplicate quantum states. So that's like one conceptual problem with quantum random access memory, but there are many other constraints. A very good source of quantum states is running a quantum simulation. So this was the original idea behind quantum computing. Going back to 1981, and the Nobel laureate Richard Feynman said that if there's any quantum mechanical system, it has just so many degrees of freedom that it doesn't matter how big our computers will ever get, our digital computers will get. They will always run out of resources like beyond a few atoms. And he said that, hey, why don't we build some simpler quantum system that we can easily control? It already has a high degree of freedom, and just use that to simulate the stuff that we are actually interested in. So it's quintessentially a quantum mechanical system, so it is a quantum state, so that's a fantastic source for quantum states. And the last one is, a quantum computer operates on quantum states. So if you already have some calculations going on and you want to pick it up from there and do some quantum machine learning on it, that works too. But there's one thing you cannot do: you cannot start from classical data and get classical data out if you want an exponential advantage. Okay, so let's see like the basic ingredients of what goes into Bayesian deep learning on a quantum computer. So the Bayesian part of it is a cool result from last fall. There were 2 papers coming out roughly at the same time that extended Gaussian processes to a multi-layer case. And they argued for an equivalence between this, basically a daisy-chained sequence of Gaussian processes and deep learning networks, with the fundamental difference of having priors all over the place. And like this connection was known for the single layer neural networks since 1994, but the extension to the deep case came only last year. It's actually very easy to do, so it's surprising that it took so long. So that's the Bayesian deep learning part. So you map 2 consecutive layers into like a very specifically set up Gaussian process. And the first author of this award-winning paper that we had already had a paper on training or calculating stuff on Gaussian processes in the quantum computer. So from there, it was fairly easy to think through like what are the new mathematical advances we would need to extend this framework. So super quick refresher on Gaussian processes. We work in the supervised regime, and basically what we have is we define a Gaussian prior, and we say that we want to calculate the posterior over this prior, and the sweet spot, that this is the sweet spot for anything Bayesian, where you want a posterior that's easy to calculate. And that's why it is so easy, because you start with a Gaussian prior and your posterior is also Gaussian. And your covariance matrix can be thought of as a kernel. And this is where your freedom enters your Gaussian process, because you can define basically a large range of kernels that would work as a covariance function for your Gaussian prior. And then your posterior update is given with a particular formula. And then this is what we are looking for, right? Here you have a big kernel matrix that we have to invert. So now we can start thinking about our quantum matrix inversion algorithm. So it has some mean that requires an inversion, and essentially the same inversion goes into calculating the new variance in the posterior. And then there are some tricks in these papers that came out a year ago, how you daisy chain these things, so you can have multiple layers of Gaussian processes following each other. Okay, so that's the classical machine learning part. And so this is what I told you, that in Bayesian machine learning we like easy posteriors that we can calculate in some easy fashion. And in quantum computers we like linear operations in general. So like nonlinear stuff gets messy. Quantum systems, like a quantum calculation is unitary, which is quintessentially linear. So every time when you want to introduce some nonlinearity, that's very tricky. So thinking in these 2 terms, you have to be very, very, very careful how you pick your covariance function for the Gaussian process. And so I don't know, what's your opinion? Like, what's the percentage of the machine learning community who are Bayesian? Give me figures.
5%,
2%, 20,
90%, 10,
1.
I would go for 1%. It's a very angry 1%, but I think it's a very small minority. And I think part of the reason is that you have to calculate a lot. So every time you have to think through like what would be your posterior and how you achieve the updates going for your prior. So it's just a lot of calculation on paper for for any kind of change in the model that you want. And it's kind of similar with quantum algorithms. So any trivial change you want requires you to go through like a lot of steps and a lot of calculations on paper. And we went through this for the rectified linear unit covariance function, just to see what it would take on this quantum computer to calculate this. But this is already like 3 lemmas and 2 theorems just to make this work. So it's a little bit finicky, but it can be done. So in that, if people like calculating on paper, and this Bayesian quantum framework is perfect. Okay, so when it comes to the actual results of this paper, there are 3 tricks going into it. But the first one is what I mentioned. So these are these two papers that appeared about a year ago. Then the actual meat of the paper is the second part. So one of these 3 papers that came out in 2013 that really unleashed this revolution in quantum machine learning was about quantum PCA. So they gave you some exponential advantage in calculating the principal component analysis. And they used like a super interesting physics trick to achieve it, which was they basically made a quantum state exponentiate itself, and then revealing its own eigendecomposition. And we modified this to come up with completely new primitives that were just not there for doing linear algebra with quantum computers before. So the 2 tricks are element-wise metric manipulation, basically calculating a Hadamard product with the same trick, and then calculating the outer product too. So these are just small changes to this original algorithm. They give you completely new linear algebra primitives using a quantum computer. So it's, in that sense, this paper is a valid piece of research. But I decided that this requires a lot of physics thinking, a lot of physics tricks. So I would not be able to tell you all of it in a half an hour. So I decided to focus on the last trick, which is the quantum matrix inversion part. And I also decided to focus on this part in this talk because this is the part that we actually implemented on a quantum computer to see how it works. And the reason we implemented only this part, because this is actually not so difficult in terms of like how many circuits you would need. How big the circuits would be that you would need. The tricky part is this one. So the rest of the talk focuses on this quantum matrix inversion, and I really hope that you guys will learn something based on that. So let's go through the main steps of it. So we have some linear equation, ax equals b. And we want to find x, but if we encode things in a quantum system, that these are going to be quantum states. And as I told you, if you actually want the state in the end, then you would have to do a full tomography. So we don't really want that. We will just sample the solution of x, and that's still meaningful in the scenario that we consider. And what we're going to do is we expand this b vector in the eigenbasis of A, and we basically just invert the eigenvalues, and that's it. That's the core idea. And so first we have to do the state preparation for B. Then we have to do a quantum simulation of A. We're going to see in a moment what that is and why we need that. Then we do a quantum phase estimation, which is a technique for extracting, which you can think of it in 2 ways. You can think of it as a way to extract eigenvalues, or you can think of it as converting between different ways of representing information. And then we do something called a control rotation. This is like the easiest step. And then we have to do something very technical, which is called uncomputation. And then this algorithm is probabilistic, so that it has a certain probability of succeeding and failing. And we have to post-select on the successful branch to actually get the result. So that's the outline. Yeah?
Maybe a naive question, but how do you sample without causing any interference? Like how do you sample stuff out of the quantum space?
That's going to go into some computation. So maybe remind me of this question. Okay. That's a technical thing. More questions about the outline? How does this program sound? Easy, no? You can just go to PyTorch and do that. All right. let's see it. State preparation. We have a couple of assumptions. This algorithm is super tricky. It's full of assumptions. And it's very easy to overlook the assumptions. And it's also super, like even the original paper. So the original paper on the quantum matrix inversion came out exactly 10 years ago. And it has four versions on arXiv, and one published paper in Physical Review Letters, which is this very prestigious physics journal. And if you look at the four versions on arXiv, all of them are completely different. There's basically zero overlap between them. And you should not look at the last version. You should look at the second last version. That's the most complete. That's like 30 pages. So you should look at that one and the published version, and you can stitch together the algorithm from these two. But it's difficult, and people know it's difficult. So in case you guys ask hard questions, I printed a 55-page paper which came out this February, which is Quantum Linear Systems Algorithms, a Primer. So basically, it explains this algorithm to you in 55 pages from scratch. It's that bad. And the journal where it was published, Physical Review Letters, has a page limit of 4 pages. So that's why it is just so difficult to grasp in its original form. The reference for the primer is here. I have a link to the slides at the end of the talk if you guys want to follow up. Okay, assumptions. We have an assumption that this A matrix is Hermitian. This is easy to relax. Like don't worry about this one. Assume that B is normalized. We need this because every quantum state is a probability distribution. Probability distributions are normalized, and therefore this B vector must be normalized. The key difference between classical probability theory and quantum probability theory is actually the nature of normalization. So when you think about a classical probability, then you know that the sum of the probabilities must be 1. And you also know that each probability must be greater or equal than 0, right? In other words, you're normalizing in the one norm, right? Now the only difference in quantum physics is that you normalize in the 2 norm. That's it. And you are no longer restricted to positive probabilities, because now your probabilities can take complex values because your normalization is L2. So you square the absolute values and you add them up to 1. So the restriction on positivity goes away. So when you think about it, if you just think of like coin tosses, then if you plot the bias, which is say probability 1, and you plot it against the other one, then it's a straight line in one quadrant, right? Just one quadrant, because you're restricted to the positive quadrant in both probabilities P1 and P2. And when it comes to a quantum state, you have this entire sphere to work on. So you're not restricted to a quadrant, and it's not a straight line. It's something curved. So that already gives you an idea of like why quantum mechanics is even interesting to look at in the first place. It's just a very different probability theory, which comes from changing the normalization. Anyway.
I mean, the probabilities are still positive. It is the probability amplitude.
It's the probability amplitude that's a complex value, but the square sum adds up to 1. That's right. Yeah.
Yeah, so the wave function is complex as a probability.
Yeah. Yeah. But all of that comes from the normalization at the end of the day. Because you can also write that in classical probability theory is the absolute value summing up to 1. It's just you already restricted them to be positive.
But that also holds in quantum physics.
That's once you measure something out, then you're back to classical probability theory, right? Okay. All right. So we just very briefly introduced the bracket notation, which is the standard notation in quantum physics. So mathematically it's very easy, because you take your vector in Rn, you put them in this funny notation, and suddenly it's a quantum state. And it describes the same thing. It's a column vector, as long as we are in finite dimensional spaces. But you also have to think about it that now it's also a probability distribution. So it's something you can sample as opposed to just being a high-dimensional vector. And I mentioned this assumption that B can be efficiently prepared. This may or not be the case. It might be a lot of work to implement it in a lab or in a quantum computer.
Is there a rigorous definition for that efficiency? Like, what does it mean?
There is, to my knowledge, there isn't, because arbitrary state preparation is equivalent to universal quantum computation. So you might need like a very deep circuit to prepare the state. And a lot depends also on like what kind of gates you have available in a particular implementation, you know, quantum compilation and all of that. And yeah, so and then we take the eigenvectors of A as these UK vectors, which in bracket notation would be this. And then we want to basically expand this B and the eigenbasis of A. Okay, quantum simulation. This is where it gets tricky. Okay, so what we are going to create is one particular type of encoding quantum classical information in quantum state, or just some notion of information in a quantum state. So what you have here is what I would call register encoding. So you have some B, and you encode it in some number of qubits to encode it into this cat. But a quantum superposition allows you to, you know, put several basis factors into probability distribution, and every time you measure it, you just get out like one of the possible one of the basis factors out. So you can. This also means that these probability amplitudes, so for which the square norm must add up to 1, can also encode information. So these are already two ways of encoding information. One coming from the probabilities that make up a quantum state, and the other one is, you know, whatever goes into this cat. So this is what I would call register encoding, and the second one is called amplitude encoding. And the third one is what I'm showing here, but it's a little bit difficult to see, and it's not in quantum mechanics or quantum computing textbooks. So this A matrix is what we want to actually invert. And what we are going to do with this is we are creating an operator of it that acts on a quantum state. In other words, the very quantum computation that you execute can also encode information. This is very unusual. And this takes a while to digest. Okay, so what we are doing here is we are creating basically a unitary operation, so a quantum calculation based on the matrix that we want to invert. And the reason we are doing this is because we are interested in the eigenvalues of this matrix. But we also know that, you know, everything is normalized, and we are working in complex spaces, which means that all of your eigenvalues will be on the unit complex circle, right? So eigenvalues of a quantum evolution are basically just different phases on this unit circle of complex eigenvalues. Are you with me on this? Okay. This is super important. So really, so just eigenvalues are restricted to the unit complex circle. Okay, then let's see what's this nasty thing here. So a quantum calculation has this like very typical mindset of having stuff that you're actually interested in and having some ancillary register attached to it. So you have a bunch of registers, including, you know, for instance, these B vectors, and you attach another bunch of qubits to it, which just help you with the calculation. So this is called an ancilla. And what you have here is like one of these ancillas. So it contains this capital T number of qubits, which is the bit width of the accuracy for which you execute your calculation. And then this will be like the probability amplitude of the quantum state that you're encoding. So the absolute value square sum of this adds up to 1. So this is where the encoding goes in. And you might wonder, like, where the hell this form came in? You know, it has sign in it and square. Like, what the hell is this?
So just wondering, the tau is like a scalar. So how do you kind of encode it in that register, encoding in the kit? So like, how does it go into the kit as well as being something in the summation?
It's an integer. So it's a binary encoding
of the integer.
Yeah.
Okay.
Yeah. Okay. One more perspective on quantum computing. So in a digital computer, you operate on bit strings, right?
Yeah.
And then you operate with certain logical gates, and it allows you to do like arbitrary arithmetics on decimal numbers, for instance. And like the only thing that you are changing really is that instead of bit strings and deterministic operations, what you have is probability distributions over bit strings. And basically that's what you have here. So these are the bit strings going from 0 to t-1 in binary encoding. And these give you the probability amplitudes for each of these bit strings. So if, for instance, if you prepare this state and then you measure it out, you would get one of these values of the bit string, okay, for instance, the full 0, with some probability that corresponds to this probability amplitude. So this one multiplied by the corresponding value. Well, that's squared. So if you keep measuring this stuff over and over again, then eventually you are able to reconstruct like every single bit string that's encoded and the corresponding probabilities.
And if you like encode the integer, like the integer tau in like a gray encoding or some other like some other bit encoding tricks, does this actually work? Like, do these weights have to be like? Is there any significance to individual qubits, or whatever you do is kind of entangled if I'm using the correct kind of quantum work?
This is $1 billion question.
Okay.
There are just so many things to it. Especially when you think about contemporary quantum computers, because what you ideally want is that any two qubits can interact. But that's not what happens in most of the architectures that we develop today, because the vast majority of quantum computers out there are superconducting architectures, which means that you are using the exact same silicon fabrication technology as you would do to create a CPU in a laptop or in a phone. That's why it is attractive, because you already have the fabrication technology. And all you have to do is just cool it down to 8 millikelvin. And then you can do your quantum calculation. But the problem here is that you cannot make arbitrary connections between any two qubits, because then the couplings between the qubits would overlap, and you can't do that. So you will always have some missing connections between qubits. And that's why it is critically important of how you encode information in this qubit when it comes to these superconducting quantum computers, because the connectivity can really screw up your calculations. Because if you have to interact two qubits that are not connected, then what you have to do is you have to swap values of qubits until the two that you want to interact are neighboring. You do the interaction and you swap things back. But one swap takes at least 3 gates. So now imagine, I told you that on the quantum computers we have today, if you do 10 gates, your calculations are just dead. There's like no meaningful result coming out of it. Now you use 3-4 swaps, you do your operations, which is 1 gate, then you do another 3. You already used up 7 gates, and you just perform 1 calculation. So your question is very to the point. It's critical how you encode information here.
But I gather, so it's critical in terms of the current technology, but not in principle. So
in principle, there are two answers to this. So this is the first one, and it's very pragmatic today. And the second one is like, how can we compress classical information to use a minimum number of qubits and all of that? That's also a meaningful question. This is something I know much less about. Yeah, very good question. Okay, so what this horrible looking state is, yeah?
I was just going to ask about that state. If you go halfway through between tau equals 0 and t-1, then that's the maximum value, right?
Yeah.
So is that by design, or?
So you're doing something.
It seems very bad. Okay.
What this state is, it's a timer. Because what's going to happen is you create this quantum calculation, this unitary operator. So on this side, you have this matrix in this. Forget about this, all this stuff around it. These are just some time steps for this A operator that we are actually interested in. And what's this here is a control. So what's going to happen here is that this control will execute this thing for certain length of time depending on this timer register. So what it creates at the end is the superposition of this operator applied to the B state at several time steps. Okay.
But where is the B state?
The B state is, so this is what you want to solve. Ax equals b. We created the B state from this B vector. So this is like the constant vector in our linear system. And basically what we are applying this quantum calculation on is this state. So the timer together with the B state. So B is described by a bunch of qubits. That's, let's say, one register. And then you have the second register, which contains the timer. So what you end up doing is basically you apply this evolution operator with different lengths of time applied to the same state. So the superposition will be this B state evolved with different lengths of time of this operator.
So essentially the result of U applied on psi 0 times B is going to be sum over tau, that exponential applied on B with that coefficient sign of whatever for different taus, right?
Yes. Yes. Okay. So this is so when you do an operation like this, it's called Hamiltonian simulation. And there's a long history of how to do Hamiltonian simulation and what are the limits of it. But in this particular algorithm, the big assumption is that the Hamiltonian is sparse, which means that your Hamiltonian is now this A matrix that you want to invert. And this means that your A matrix cannot have too many non-zero elements. Okay? It has to have like largely zeros, and that's when it can be efficiently simulated.
What is large?
But how sparse?
Yeah, that's.
So the error bounds and stuff in this paper depend on that. But like it's like the scaling is terrible in terms of sparsity.
That's why you're using ReLU.
No. That's not why I use ReLU. That will come. That's in a different part of the algorithm why we need ReLU.
But do they need to always be the same weights? Do they need to be sparse?
No.
So
Like
you can do like drop out, right? In one round you set all these to zeros, and the next round set the other ones to zeros.
That's a good idea for a paper.
And then you do it over and over and over again. You can train all the weights.
I'm not sure. So I realized that there's a conceptual difference between how you think about a quantum calculation and you think about a classical calculation. So classically, you're just so used to pulling in a bunch of elements from the memory, executing some arithmetic operations on them, and then writing them back to memory. A quantum calculation is different. In a quantum calculation, like whatever you want to express is always global. Your entire problem has to be on the quantum processing unit at the same time. And this is very different. And so, for instance, when you think about just searching an element in an unsorted set, right? So you have some minimum number of lookups. Like you have to look at every element because it's unsorted, so you don't know like where is the element that you're actually looking for, or where is the minimum. So, say you are in a discrete set. But in this famous quantum algorithm from 1995, Grover search, which gives you a quadratic speedup to this, you basically put all possibilities into superposition, so everything is available to the quantum computer, and then you do some quantum evolution to steer the probability distribution to the element that you're actually interested in. But the information is global, so you don't go through it one by one. This is a major conceptual difference. So that's why I feel it goes somewhat wrong because like this matrix inversion is always a global operation. Like you can't do it in small chunks. That's why it's hard to do on a classical computer. That's why it's expensive to do on a classical computer. Tell me.
Well, like, okay, I mean, you're way far beyond my understanding of things, but I'm sort of following along. But so the idea is that you're trying to create a pulse, right? Effectively, and the pulse is measuring, in some sense, the evolution of the overall, as you're saying, of the global state, right?
Yeah.
Well, the thought I had was that, I mean, on some level, that kind of is dropout in a global space, right? Because what you're effectively doing is you're saying, okay, give me a sample of the global distribution, okay, over one expression of that evolution, right? And then you're saying, give me another one over that expression, right? In some...
Yes, but that's not what it's going out for.
Okay.
So what you're going to create is you're interested in the eigenvalues.
Yeah.
But the eigenvalues are just different phases of the same unit circle,
right,
in the complex space. That's what we are aiming for. So you want to be sure that you can extract all eigenvalues at the same time.
Oh.
That's what you want.
Okay, so it's the same, it's just different parts of the same object, or in some sense.
Yeah.
Okay.
It's a little bit difficult because it's a superposition of like a temporally differently evolved stuff.
Right.
But it's still just a superposition.
Right.
Just to make sure I'm understanding correctly, so the U is not the Hamiltonian. If a system's Hamiltonian is A, T0 time steps, or like after T0 time, the operator governing like input to output would be the U that we have there. Or U itself is the Hamiltonian that we are kind of like...
Here, like the Hamiltonian that they're interested in is this A.
Is A, and that is like integrated over like T0 time, or T...
Integrated over...
In fact, yes. It is an integration over 0 to T0, but A is constant in time, so it just comes out of the integration.
Yeah.
But in general, yes, U is an e to the integral of...
I mean, yeah. So U is the solution of the Schrödinger equation.
Right.
Yeah.
Okay.
So you
start with whatever state at T equals 0.
Yeah.
And you apply U. You'll get the state at T
But
equals
evolved,
T
yeah,
sub
from 0 to some time T. That's right. That's exactly right. Yeah. Okay. From here, it's gonna get easier. So if you are lost, you are going to get it in a. Once you see the circuit, you're like, now I understand.
So if you want to wrap up this slide, the answer to why do we do this is.
So that's why you have to look at the circuit. So I knew it's going to be a bit of a back and forth between the different slides, but I just couldn't find a better way. So if you're completely lost, this is a good time to come back and pay some more attention. It can be understood. Okay, so what you are going to do is this quantum phase estimation, which is going to be at the end of the quantum phase estimation. This is the state that you are going to get. So let's look at what this guy is. So you have here the eigenvectors of the A matrix, but most importantly, you wrote the eigenvalues of the A matrix into a register. And that's what quantum phase estimation does. So previously, it was somehow encoded in the phase, in the probability amplitudes. And now from here, like before these column vectors, it was here in the probability amplitudes, and now it's written there. That's the game we are playing. That's what we want to do. We want to transform representation of information from probability amplitudes to the register.
Another question: would it be correct if I say this is basically what you want to do in this step? Is kind of a quantum version of the power iteration? So you have an eigenvector. You want to find the corresponding eigenvalue. You just kind of repeatedly multiply by that vector and take the quotients. Is that what you're trying to do? Because I don't understand anything on this slide, but that's like the way I'm conceptualizing
I think that would be some convergence And that's not what's going on here.
So this is exact.
Okay, sort of.
Sort of.
It depends. It depends on your how many bits you use to represent the eigenvalues. But it can be expanded exactly in binary.
Can you define U? What is U?
So this U is oh sorry, yeah, it's not the same U as this. It's just this part. I bet.
Okay.
Yeah. So we are looking for the eigenvectors of that. So now, okay, so now come back if you are completely lost. This is the moment to understand it. So now we are applying this U, which is, this part here, and this C is the control part. So the C is this part. Okay, so here U to the second means that you evolve this unitary operator for a certain amount of time. Here, this is U to the first power, which is just U. This is U squared, U cubed, and so on. So this is what I said, that you have U's at different lengths of time. So integrating the Schrödinger equation at different durations. And you apply the control on them. So what is the control? The control means that if the control bit is 0, then you don't do anything. You actually don't apply the unitary. And if the control is 1, then you apply the unitary. But here you have qubits, which can be superpositions of zeros and 1. So you can create this superposition between applied and not applied. And that's the game that you're playing. So you input the deterministic 0 state, and you send it through a Hadamard gate, which creates this equal superposition of 0 and 1. So now it's 1 with 50% probability and 0 with 50% probability. And that gives you the control for this unitary. So now this unitary is both applied once, and once it's not applied. So you create this superposition of both.
So is the H the same as A? Now that U is not really the U that we had, I think.
So H is the Hadamard gate. It's the name of the gate.
Okay.
Yeah. All right. So the game that we played so far is that we created U at different time intervals, and now we are creating this full superposition of applying it and not really applying it, right? And what this allows us to do is to have the phases or the eigenvalues as probability amplitudes in a superposition. So now you have the superposition of the eigenstates of this operator, and you can expand it in this eigenbasis. You have every single phase that you are interested in as probability amplitudes in the state. And now what you want to do is extract these phases and write them into the register. And that's what quantum Fourier transformation does. It's actually an inverse quantum Fourier transformation. So you take these probability amplitudes, which encode all the information that you want, and put them into a register.
So the H's are actually discrete Hadamard gates?
Yeah.
Or so it's not the same gate so this is happening all in tandem?
Yeah.
Over time, I guess, because of that sampling.
Well, when you implement it in a quantum computer, there would be some delay between this and that. But in principle, they are applied independently on these qubits.
And then you're basically just extracting out the components with the inverse.
Pretty much. Yeah.
Transform. Okay.
Yeah. So at this point, you have this full superposition of all the eigenvalues as probability amplitudes, and at the end of it, you write them into the register. That's the tricky part.
But that's still in a quantum state.
Oh, everything here is a quantum
right.
state. Or when you see these signs, these are measurements. So when you do measurements, then you extract some classical information, but that's needed for like the quantum Fourier.
So, what is the operation that you perform on those solid circles? Like, what are those black dots?
Are these guys?
No.
The black dot is the control.
Oh, it's
so that means that it controls this operation.
So essentially, the line there is an equal superposition of 0 and 1,
Okay.
right?
Yeah, after the Hadamard gate, it's an equal superposition of 0 and 1.
So the Hadamard controls the bottom operation, not the other way around.
No. So let's go through this.
Okay.
So you send in the 0 qubit,
Yeah.
the Hadamard gate, which means here it's an equal superposition of 0 and 1.
Zeros and ones. Yeah.
Yeah, and that controls, so this is the control part, this unitary.
Oh, okay.
So after the black circle, the state that you have for the first two lines is 0 times no operation on the bottom line,
Okay.
plus 1 with operation on the bottom line.
Okay.
Sort of like an entangled state at that point.
Okay.
And you just keep doing this for everything. So at the end, you will have nothing applied, then just the unitary applied once, and then the unitary applies on the time steps. So like you have everything in the superposition in the end.
I kind of get it. Yeah.
Yeah.
Okay.
But doesn't this mean that the bottom line should be like n size of n, right?
Yes. So this is like this psi here now is your B vector, right?
Okay.
So whatever, how many, depending on how many qubits you had to describe that, is the same. All right. I think many people managed to get over this hurdle. Anyway, so the end of so this is where the simulation goes into to create these unitaries, and then you have this like trick of controlling the unitaries, which then goes into this black box, which I call the quantum Fourier transform, and it's actually this point where things go really, really wrong.
I'm confused about it. You said that you tested this in IBM. They have only like 10 qubits.
I'm getting to the experiments later. Don't rush ahead. So this is where this thing goes wrong, because this quantum Fourier transform is the exact same operation that you have in Shor's algorithm, right? So it's this primitive that you need, for instance, to factorize a prime number, and this is this circuit that needs at least quadratically many gates to run. So if you want to break 2024-bit RSA key, that means that you need at least that many qubits. 1,000 qubits would be awesome to have. We have like 16. But suppose we have the 1,024 qubits, and then you would have to be able at least quadratically many gates to run the quantum Fourier transformation, which would give you 1,000,000 gates. That's where things go really haywire with this algorithm. It's this black box here. All right, from here it's easy.
Sorry, did you say what n was in that expression? N is the number of answer
N is the number, now it will be capital T, which is the size of the ancillary register.
I see.
Okay.
So which is log T, or which is log of capital T, or the ancillary
T.
register?
It's not T.
Is it T or log T?
It's T.
Because aren't we going
That's
up to
your precision.
Yeah.
Of your bit rate. So here there is no difference between like digital way of encoding a number and like it's just the same bit string.
So can
So
we
if
go
you-
back
if-
like a few
yeah.
slides? I just have a question. Maybe I completely got it wrong. So
Yeah.
that summation involving the sign, that went from like 0 to T, and you said that you kind of like get the bit encoding of the integer
Yeah.
and put it in the quantum state. So in that case, if the index of summation goes to like T minus 1, then we only need log of T minus 1, or like this.
Yeah.
Oh, yeah. Okay, so let's go through this. Let's go through this. So imagine that you want. Okay, I think in terms of bits. So you want a 3-bit precision. Then this T this tau would go from 0 to 7. Yes, you're right. It's logarithmic. Yeah.
So.
But it's the exact same as you would do in a digital circuit. The same representation of numbers.
So if you need 3 bits, T should be 7. So 2 to the 3 minus 1.
Yeah.
Okay.
So that in that sense, it's logarithmic.
Okay.
Yeah. It does nothing fancy quantum here. This is just encoding
Straight up.
a decimal number in a binary string. Yeah. Okay. All right, so remember at the end of the calculation, this is the superposition that we have. So we encoded the eigenvalues here, and now we want to invert them. So what are we going to do? So that was this question about whether measuring stuff out can interfere with stuff, and the answer is yes. So what we are going to do is we have to get rid of this register, the value of this register, because we didn't talk about something called entanglement, but like this full state can be very entangled. And if you start measuring stuff out in just a single register in an entangled state, that can have like the detrimental effects of other qubits that we are interested in. So first we have to uncompute this. And this uncomputation is a very unnatural concept if you come from a classical background. In a quantum computer, every calculation is reversible, like strictly reversible. Whereas in a classical digital computer, even your most elementary sets of gates are non-reversible. If you apply an AND gate, you cannot really reverse it. You lose information, right? So if your answer after the AND gate is 0, then you don't know what your two starting bits were. In a quantum computer, everything is always reversible. So because of that, when you have some quantum computation encoded by a unitary, just by taking the conjugate transpose of that unitary and applying it on the same state, you end up with what you started with. So to avoid problems with entanglement, you actually have to apply everything that went into creating this state in reverse. So to get rid of it, and now you can look at the rest of your state as unentangled to this register, and then you can use that as the result of your calculation. So we apply this control rotation, which is something ridiculously simple. You add one more qubit, and you do a particular type of rotation, and you end up with this state. So this state is almost the same as you saw here, except this like extra element of superposition. So with some probability, you get the 0 qubit here in this extra register, and with some probability that's proportional to the inverse of the eigenvalue with probability 1. So now we are getting there. Now we are really almost there. Because now, if we uncompute this, so we make sure there is no entanglement in the entire state, and measure the ancilla thing, and if we get 0, we just throw away the whole thing and restart from scratch. But if we get the output 1, then we know that the rest of the stuff is proportional to the inverse of the eigenvalue multiplied by essentially the B vector. This is just the expansion of the column. So we already got rid of some register here, but basically the rest is just proportional to the inverse of the eigenvalue times the B vector.
So where does the C come from? Is it like a partition function, so it just normalizes stuff?
That's to normalize the quantum state. That's right. Because the L2 normal of this vector still must be 1. So it's there for normalization. You can calculate what it is, but it's just an ugly expression. So
but isn't it critical if you want to see what the lambdas are? Like, don't you need to have that with some precision?
Yeah. You have to have that, but it's something that you can calculate very easily. It's tedious, but it's easy to calculate.
So what is K?
K is the J.
Of course.
I don't know what it is. Okay. All right. That's the full algorithm. So once you do this post selection, so you measure out, you get the answer 1, then you know that you can use the rest of the state as the result of your calculation. So you inverted the matrix, and then you can start sampling them. So where things go wrong, like one is the circuit depth, very bad. The second one is that the accuracy of this algorithm largely depends on how well conditioned your A matrix is. So it doesn't. First of all, it has to be sparse, otherwise you can't do this trick with the different time evolution. And second, it has to be well conditioned, so the ratio between the largest eigenvalue and the smallest eigenvalue cannot be crazy. They have to be roughly on the same scale. Otherwise, your error terms scale very bad. They scale quadratically with the condition number. And then the size of the ancillas in the error terms is also very bad. So whatever ancilla register you saw before, like that's the part where you really need as many particles as there are in the universe to invert a 20 by 20 matrix, right? So that's where it becomes really unrealistic. And that's why I was so upset about all these papers coming out using this algorithm as a primitive. And then now we arrive at the implementation, right? So here's what we did. We created a simplified circuit. Like we went through all of the stuff and we simplified the circuit as much as we could to invert this gigantic 2 by 2 matrix. Okay? And we wanted to see, like, you know, the promised land, the exponential advantage of inverting the matrix in 2018. And this is really where the like people who understand quantum machine learning get the joke, but most people just don't. So I was talking about post-selection and having some probability of getting the right answer, right? Because if you get the incorrect answer frequently, then you have to run it like over and over again. So we measured this success probability. So that success probability is the probability of getting 1 at the end of the calculation. Okay? And we threw different noise models at this I think that inverting this 2 by 2 matrix with ancillas and everything, it was 8 qubits. We needed 8 qubits to run the protocol. And so, you know, we threw noise models and we see that, you know, if it's more noise, then your success probability goes down. Fair enough. You know, nothing special. Then first we implemented it in Pikeville, which is the programming language that's used to program the Rigetti quantum computer. And that's where we tested the noise models. We were very happy. And, you know, NIPS submission was just 2 days away. And we were begging Rigetti, hey, give us computing time on your quantum computer. We want to test our algorithm on the hardware. And they were like, oh, we would be very pleased to give you access to our quantum computer, except that our refrigerators failed last week. And our quantum computer is, instead of being at 8 millikelvin, it's at room temperature. And that was an unpleasant moment because suddenly we had no results to show for NIPS. And then they said that, okay, but don't worry, we have this old quantum processor, our previous generation, which has just 8 qubits and a very crappy gate fidelity and whatnot, but you can use that. We're like, okay, just give us access. And it was perfect because we were using 8 qubits anyway for our protocol, so it was a perfect fit. But the problem was that was connectivity. So this 8 qubit chip is linear. So like one qubit is connected to the next, and the next, and that's it. So the two ends of, and okay, it's a circle really. So the two ends are connected, right? But then you have to do all these swaps in the middle to do all the calculations we wanted. And then we had to sit down again, redesign the entire circuit to get rid of as many swaps as we could. And then we still ended up with 2 swaps. And I told you, right, like one swap is 3 gates. So that already used up 6 gates, and we had like a lot more gates to run. So in the end, like once we put together the circuit again, we ended up with about 16 gates or so. And we threw it at the actual chip, and we got exactly 50% probability of getting it right. It's just conflict, right? And the problem is that you can translate this success probability to something called fidelity, which measures the overlap of how close your quantum state is to the quantum state that you want. Okay? And if you translate this to fidelity, to overlap to the target state, you end up with 0. In other words, the calculations that we performed had absolutely no connection to the actual inverse of the 2 by 2 matrix. That's your exponential advantage today. And this is the joke that most people just don't get. Like Rigetti was so happy with it. Like, hey, write us a blog post on it. Like, okay. And then we tried IBM. And the thing about IBM is that the hardware is much better, and the refrigerators don't fail, but the software stack is absolutely horrible. It's unusable. And Riget has all sorts of nice tools built in that help you design the circuits, and it liberates you from a lot of the work. And on IBM, like, you really have to do everything manually. And okay, so when we were desperate, we just spent the night like rewriting everything for the IBM stack because we really wanted to submit it to NIPS. So in the end, we got the results on both computers. So on IBM, we got some 84% or something like that, which translates to a fidelity of 76%, which is still extremely low, because for any reliable quantum calculation, you would need something well above 90%. So there goes your exponential advantage. So this is how unrealistic a circuit is. You can't even invert a 2x2 matrix today on real hardware. And the hardware is evolving rapidly. And there are lots of fun algorithms that you can execute and get decent results. But quantum matrix inversion is not one of them, and it's going to stay like this for many years to come. So basically, that was the punchline in our very well conceived joke that unfortunately nobody gets. That's it. So if code is easier for you to understand than all this mathematics and linear algebra and the strange formalism, then we have it open source and the MIT license, so you can integrate it in your pipeline. And as I said, the slides are also online. Every other Thursday, we have a quantum lecture in the Vector Institute, if you happen to be affiliated one way or the other. The idea is this, to go through very slowly about on quantum computing and quantum physics concepts, so the machine learning and the deep learning community can understand it better. The next talk is going to be on Thursday by Roger Mackel. He will talk about quantum manipulative physics. And then at the end, well, in mid-December, we have like a half-day quantum computing, quantum machine learning workshop. It's mainly for like business community, but there are going to be technical talks too. And I'm creating the very first MOOC on quantum machine learning, focusing on not on this abstract stuff, but the stuff that you can use today on quantum computers. So if you are interested in beta testing the material I'm developing for this, then just send me an email, because I really want to make sure that this material is digestible for people with your background. And there's just so much bad stuff out on quantum machine learning that is completely unreliable, that two of us sat down and wrote up something that we feel that's realistic in terms of timeline and what's possible today. So it takes 12 minutes to read, but that's still shorter than this talk I'm giving now. And there's also a LinkedIn group if you guys are interested, just join that. So I'm going to leave a bunch of questions here. So the quantum computers that we have today require mainly something called variational algorithms. So these variational algorithms do a very short calculation on a quantum chip, which are shallow because you cannot use many gates. Then go back to the classical computer. The classical computer does some post-processing and tunes some parameters in the quantum calculation, runs the quantum calculation again, and you keep going back and forth between the quantum and the classical part. So these are called hybrid quantum classical algorithms or variational algorithms. And there are ways of extracting eigenvalues with these variational algorithms. But so far, I haven't really seen like a full-blown protocol for matrix inversion using these. So I think that's a fun question to ask. Then, people have Bayesian methods because of these things I mentioned. They just take a lot of calculation on paper. And then with quantum computing, we had these new constraints that you can't just consider any covariance. Your covariance has to be in a very specific form. Like, what's the actual form? Well, take a look at it on paper. I didn't go through that part. But maybe we can think reverse, because there are some covariance functions which are natural fit to quantum computers. And maybe you can reverse engineer from there and come up with some new Gaussian process fitting the quantum computer, as opposed to trying to force an existing classical kernel on a quantum computer, which is actually difficult to calculate. And yeah, that's about it. More questions?